Thank you guys for being here. We're going to continue our discussion of nested loops today. All right, so you remember last time we ran through a couple of algorithms using nested loops. One was to print a square, an n by n square, and the other one was to make a right triangle, which was kind of n by n, but only half the square, if you want to think of it that way. So I have that one up on the screen now. It was function triangle, and remember, if I said triangle 4, I get 1 0 on the first line, 2 zeros on the second line, 3 zeros on the third line, and 4 zeros on the fourth line. The code we came up with was this. We said, oh yeah, it has to be at least 0. We had 2 loops. Traditionally, we have an outer loop and an inner loop. The outer loop oftentimes has a dummy variable of I, or control variable of I. The inner loop has a dummy variable of j. And in this case, we let I go from 1 to n, so we're going to print n rows. Each time we're printing a row, we do the inner loop. Remember, the I stays at 0, and while I is at 0, j goes from 1 to 2 to 3 to 4, whatever it has to do. And then I goes to 1, and we do it again. You have that picture of the wheel inside the wheel. Okay, but in this case, to make it a triangle, on the inside one, instead of saying j goes from 1 to n, we said j goes from 1 to I. So when I was 1, we went from 1 to 1. When I was 2, we went from 1 to 2. When I was 3, we went from 1 to 3. Exactly what we wanted for this guy up here. Okay? We're caught up. All right. Now, I know what you're all dying to do. I don't blame you. I was once in your shoes, so you want to do a statement execution count. Am I right? Yeah. It's like, I could go home for Thanksgiving or statement. So we're going to do statement execution count. Yeah. Well, if you're reticent about this, it's actually a good. Your spider senses are working well. This one's a little bit more dangerous than the last one. So it's a little bit tougher, but it's good. So let's work through it. Well, the first part is easy. How many times do we do the assertion? Once. Not in a loop. This one's not so bad. How many times? Oh, remember when we did the for loop, we had to do each of these independently. So this is going to be 3 different ones, right? How many times do we say let I gets 1? Remember this? We did this last time for the square one. Everyone agree this is 1, right? Because when that first statement in the for loop happens once before the loop starts. So it only happens once. All right, so good. The first one, let I gets 1, happens once. How many times, I ask you, do we say I is less than or equal to n? Based on n, right? Because we don't know how big n is, but is it n times? Higher, lower? I heard someone say n plus 1, which is correct. This is that case where you have to allow for the failure, right? Because it actually does a test when it's too high. So if n is 3, it's going to work when I is 1. It's going to work when I is 2. It's going to work when I is 3. It will actually test it when I is 4. That's when it fails. You have to count the failure. So you're doing 1 more than the n. So you get n plus 1 times. Okay, good. And the I plus plus, how many times? Right, it's n times here. The I plus plus is just like any statement inside the loop. It happens at the end of each execution of the loop. So it's always going to go 1 less time than the test, right? Because you don't count the failure for that one. If it fails, you never reach that part. Okay, so that's kind of review. That's the same as the last problem. Where it starts getting really funky is inside the loop. All right. Okay. Let's start. Well, again, I think we did this order last time too. The easiest one is down here at line 43, so let's get our easy ones first. How many times do you do this console log? Oh, I got too far. So in other words, does this inside loop impact the console log at all? No, it's outside of that loop, so it's just, so ignore the inner loop altogether. If I just had something inside of this loop, how many times would it execute? Well, it would execute when I is 1, it would execute when I is 2, when I is 3, up until when I is n. So it's a total of n times. All right, so this I++ and the stuff inside the loop always match. Okay? Unless it's a second loop, right? That's when you start running the problems. Okay, so here is that second loop. How many times do we say let j gets 1? One time for a j loop. N times total, because we're running that j loop. The j loop is inside of the I loop, right? So everything inside of the I loop happens n times. So we're going to run this whole j loop n times. Each time we run the j loop, we're going to say let j equals 1. So we do that n total times. You guys see that? Okay, here's where it gets a little harder. How many times do I say j is less than or equal to I? How many times do I actually make that test? I think we did the statement execution count up here. It came out to n times n plus 1. It's not going to be that here. I'll warn you. Why? I mean, it kind of makes sense. This one is n to n. You do n times is almost n squared. This time we're not doing up to n each time. We're doing up to I, and that I changes each time. All right. So there's no pithy answer we can give right away here. We're gonna have to think it through a bit. So what I like to do in this is just imagine what the I is going to be each time, and do it step by step. All right, so the first time through the I loop, I is 1. Okay, so when I is 1, how many times will we say j is less than or equal to I? Is it once? It's actually twice, right? Because it succeeds once, it has to fail. For the loop to stop, it has to fail. So it's going to be j is 1, and then j is 2. When j is 2, it fails. All right, so when I is 1, it takes 2 steps. But then we go back to the I loop and I becomes 2. When I is 2, how many times do we say j is less than or equal to I? Yeah, because j is going to start at 1. 1 is less than or equal to 2. Then j is 2. 2 is less than or equal to 2. Then j is 3. That's where it fails, but you have to count that failure. So it'll be 3 times. So in total, when I was 1 and when I was 2, we had 2 times. And then another 3 times. I'm going to put these closer together, so it's going to be kind of long. 2 plus 3. But then I have to do it again, right? Because I now becomes 3. When I is 3, we say j is less than or equal to I. J is 1. 1 is less than or equal to 3. 2 is less than or equal to 3. 3 is less than or equal to 3. It fails when 4 is less than or equal to 3. So you do 4 total steps then. Do you see that it's going to be 2 plus 3 plus 4 plus 5 plus ... When does it stop? When does it stop? How big does I get? What's the biggest value I is going to have? Well, I mean, we don't know, but it's big. I is going from 1 to n. If we just say it's n, the biggest value I is going to be n. So we're at the last time we're going to go from 1 up to n, but then also do n plus 1. Okay? What's it going to be right before that? Before I is n, it's going to be n minus 1, right? And so when it's n minus 1, you're going to go 1, 2, 3, blah, 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 all the way up to n minus 1, and then fail on the nth time. All right, so it's going to be 1 plus 2 plus 3 plus ... plus, I'm sorry, 2 plus 3 plus 4 plus ... plus n plus 1, this last one, the n plus 1, is when I is n. Okay, do you follow that? Any questions? So I don't want to just assume that you buy it. So if anyone has questions, it's the time to ask. Blind faith? I like it. Okay, well then let's try this J++ one then. Okay, it's going to be similar logic, but just slightly askew. I'm going to make it small so we can fit it on here. Okay, so now, how many times do we say J++? Well, again, it depends upon what the value of I is. The first time through, I is 1, so we're going to say J gets 1, J is less than equal to I, 1 is less than equal to 1. That succeeds, then we do J++. Then J is 2. Uh-oh, that's when it fails, so we don't do J++ a second time. Do you see when we start, when I is 1, we only do 1 J++. How many do we do when I is 2? Twice. When I is 3, 3 times. When I is 4, 4 times, right? Because when I is 4, we're going to say 1 is less than or equal to 4, 2 is less than or equal to 4, 3 is less than or equal to 4, 4 is less than or equal to 4. When 5 is less than or equal to 4, we don't J++ again. All right, so each of the first 4 times we had the J++, but the 5th time we don't. So it's going to be 1 plus 2 plus 3 plus ... plus the biggest I is n. We're going to do it n times at that time. Okay. One more statement to do here, and then we're going to have to make sense of it all. Okay, a right statement. That's inside both the loops. Kind of a shortcut you can do here. Remember that what's inside of the loop always matches the plus plus guy. So we already figured out that it's 1 plus 2 plus 3 plus blah, 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 plus n. Okay, so this one is also going to be 1 plus 2 plus 3 plus ... plus n. And you can reason through that the same way. When I is 1, 1 is going to be less than or equal to 1, so you come inside the loop and you do the right. But then when it gets to 2, you don't get n the second time, so you just have 1 the first time. When I is 2, 1 is less than or equal to 2, do the right. 2 is less than or equal to 2, do the right. 3, skip it. Right, so it's 1 plus 2 plus 3 plus all the way down. Okay, so now the problem is, ultimately, we want to make a total. Yeah, it's a little bit messy though, right? How do we get a total out of these guys? Okay, there's a trick. Unfortunately, it's going to be a little bit of memory on your part. Okay, so I'm going to make an assertion down here, and then we're going to do a little mathematical proof. But check this out for now. Assertion. 1 plus 2 plus 3 plus ... plus n equals, does anyone know this trick?
N squared plus n divided by 2.
That's right. So it's in other words, n times n plus 1 divided by 2. All right. Have you guys formal methods? Everyone's favorite class, right? How have you guys done proof by induction yet? I kind of think it's a little early for you. All right. If You would remember. So anyway, I'm going to do one for you. So but I think at the end of the semester, you're going to do proof by mathematical induction, which is a technique for proving things, general concepts like this. So what I'm saying here is if I add up the first n integers, it's always n times n plus 1 divided by 2. How do you prove that? Well, you could kind of just plug in some numbers, right? You could say, does it work for 3 when n is 3? What's 1 plus 2 plus 3? 6, right? What's 3 is n, right? So 3 times 4 is 12, divided by 2 is 6. Oh, it works for that. Does it work for 4? 1 plus 2 plus 3 plus 4 is 10. 4 times 5 is 20 divided by 2. Oh, it works again. So it must work, right? But I mean, that's proof by example. That doesn't prove anything. It proves for the certain ones you look at, right? If you could do that an infinite number of times, then you've kind of proven it. But you can't do it an infinite number of times. There's always one more. The next one could be the one that fails. All right, so there's this technique for proving things like this. And it's pretty important in computer science, so I guess I kind of want to do a quick test for you. Let me just make sure that you have this for testing purposes in this class. I am not going to ask you to do a proof like this on the final exam. So this is more for just for your benefit for today. If you are taking the Math 220 class now, you're going to do this. And Dr. Warford may ask you to do it at some point. So this should just be a first glance, and we'll get back to it later. All right, so anyway, here's what we do. To prove something like this, we first prove a base case. And I'm going to say the base case is n equals 1. Okay? So kind of like what we did before, where I just picked 3 and 4. I showed it work there. I just got to pick the easiest case here, right? I'm going to say, is the sum of 1 plus da-da-da up to n, that would just be 1, right? Does 1 equal 1 times 1 plus 1 divided by 2? So if you do the math, on the right-hand side you have 2 divided by 2, which is 1. So 1 equals 1. And you check that off. Say yes. Okay, so it's a base case. So basically we say this works, this does work at some point. Now, what we kind of do next is we're kind of showing that if that's your base case, if that's your first step in a ladder, can I keep climbing up the ladder, and based on this proof, can I prove the next one? All right, so what you do is you say, assume that 1 plus 2 plus 3 plus ... plus k equals k times k plus 1 divided by 2, and show, next line, and show that 1 plus 2 plus 3 plus ... plus k plus 1. So I'm doing 1 further, equals the next guy in the sequence, right? Which would be k plus 1 times k plus 2 divided by 2. Okay, so let me kind of reason through this for a minute. Okay, I'm saying if I can show that it works at some point, and then I show that if it works at some point, it also works for the next point, then it will always work. All right? So this is saying it works for 1. Then I say, okay, if it works for 1, then it must also work for the next one. The next one is 2. But then when I show that it worked for 2, by the same reasoning, if it works for 2, it's got to work for 3. And if it works for 3, it's got to work for 4. And so it's just showing that whenever you have one that works, it works for the next one. And that way you keep kind of going towards infinity. Right? Sorry, some of you guys in the back can't see, so let me put that higher on the screen. Okay, well, buy it or not, we're going to take just a little bit of time to show it here. All right, so this is called, by the way, the inductive case. All right. Okay, we will show that 1 plus 2 plus 3 plus ... plus k plus 1 equals, it's going to look too much like formal methods here, I apologize, but I won't put the hints. What does this equal? Well, we don't know without the k's, except that we are assuming here on line 58 that 1 plus 2 plus 3 all the way up to k is k times k plus 1 divided by 2. You see that this guy starts with 1 plus 3 all the way up to k, right? So we can just substitute this first k terms with k times k plus 1 divided by 2. All right? So if we assume that that's true, then this thing just equals k times k plus 1 divided by 2 plus k plus 1. And in fact, at this point, I can take off those parentheses. They don't, because it's part of the sum. Doesn't matter. Just like that. Okay, well, is that true? Well, I mean, it's, yeah. If we assume it's true, then this is true. Now, can we simplify? What we're going to get here is, let's see, k squared over 2 plus k over 2 plus k plus 1. Did I do that right? Simplify that. You get k squared over 2 plus k over 2 plus k. That would be 3k over 2 plus 1. What happens when you expand this guy? What's k plus 1 times k plus 2? That'd be k squared plus 3k plus 2 divided by 2. So what is that? K squared over 2 plus 3k over 2 plus 2 over 2. That's this guy, right? This guy is, in fact, k plus 1 times k plus 2 divided by 2. Okay, so that's a general proof. Okay, so once again, what I showed is that it works for 1. What this shows, what the second proof shows, is that if it works for 1, it also works for 2, which means that if it works for 2, it also works for 3, which means if it works for 3, it works for 4, all the way up to infinity. So it always works. Okay. What's that? First time I got applause on a okay, so anyway, good news for you is you do not have to replicate this on an exam, okay? If you just want to buy it and say, that's great, that's great. But what you do need for the exam, and what you do need for your upcoming homeworks, is the basic fact that anytime you have the sum of the first n integers, it is equal to n times n plus 1 divided by 2. Okay, so you need to memorize this line right here. Okay, no way around it. Because what we're going to do is when you do your statement execution counts, you're going to end up with things like we have up here on line 40. Well, look at that. You actually have a 1 plus 2 plus 3 plus da 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 plus n. You need to be able to convert that into a simpler expression. And it might help as well if you simplify this guy. That is n squared over 2 plus n over 2, right? If you just multiply through by n and divide by 2, you get that. Okay, so what I'm going to do, oh, question, yes?
Can you scroll down a little bit?
Yeah. No problem. Okay, so now here's what we're going to do. I'm just going to rewrite these lines here by substituting these guys out, okay? So actually, I'm not quite sure what to do with this guy yet, so I'm going to leave it blank for now, but let's do the third one. I have 1 plus 2 plus 3 plus da 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 plus n. You just memorize that that is n squared divided by 2 plus n over 2, all right? So this guy here will be n squared over 2 plus n over 2. All right? Here, actually, just to make it easier, I'll just replace the original guy here, right? N squared over 2 plus n over 2. Also, on the right statement, that's also a sum of 1 up to n. So I can replace that with n squared over 2 plus n over 2. Okay, now, what about this mess here?
N plus 3 times n plus 1 divided by 2.
I don't think that's quite right, but let's see. You might be right. I can't work out the math in my head.
Do you know the story of Gauss?
What?
The Gauss equation?
Oh, I see what you're saying.
Yeah.
Here's the way to handle it here. Okay. Let me it's going to be easiest on the board, so let me turn on the light real quick. If I have 2 plus 3 plus 4 plus everything up to n plus n plus 1, the key is to find our expression, all right? The one thing I'd like you to memorize is the sum from 1 up to n is n squared over 2 plus n over 2. Is there a sum 1 up to n in here? Well, almost. There's two up to n here, right? We're just missing the plus 1. Or are we, right? You see the plus 1 on the side, down at the end?
Yeah.
You know that addition is commutative, or in formal methods terminology, what's that? Symmetric, right? You can flip the order of these, no problem. So I can move this guy over here. So if I rewrite this, this is 1 plus 2 plus 3 plus da 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 plus n plus another n. And now I have my expression here plus another n. So I'm going to have, by memorization, n squared over 2 plus n over 2 plus n. And if I do the math on that, that's just n squared over 2 plus 3n over 2. Right? This is n is the same as 2n over 2. All right? So that's the toughest part, but you need to be able to identify that and do it, okay? So we're going to say this is n squared over 2 plus 3n over 2. Okay, if you're able to do that, now we put it all together. What's our total? Count up your n squareds. Well, we have a half of an n squared here, another half of an n squared over here, and a third half of an n squared over here. All right, so we have 3n squared over 2. How many n's do we have? Well, here's one, here's a second one, a third one, 3n over 2, plus another n over 2, that's 4n over 2, that's just another 2n, so these are 2n, so we had 1, 2, 3, 4, 5, basically. And then an n over 2 over here, and another n over 2 down, just another n over here. All right, so we had 5, we have 6, we have another 6.5 n, right? So that would be something like, how do you put that in halves? 13 n over 2. That's how many ones? 1, 2, 3. All right, so our statement execution count is not as pretty as it was before, right? But it's 3n squared over 2 plus 13n over 2 plus 3. Okay? Do you remember last time when we did our statement execution count of the square? We came up with 3n squared plus 5n plus 3, and we said that was big O n squared. Do you remember what the big O means? It's like if you let n be sufficiently large, kind of what's the limit of this guy's go to infinity, right? So the 3 and the 5n, that's so it drops away. We just care that the biggest thing is n squared here, all right? So its order of complexity is n squared. That big O means order of complexity. Well, this guy, as ugly as it is really the same thing. As n gets larger and larger, we don't care that we're multiplying n squared by 3 or dividing by 2, or we don't care that we're multiplying by 3 halves, basically, right? Or these guys will drop away. It's the n squared max. So this really comes out to essentially be n squared. All right? So it doesn't matter. We have a more complex loop this time. If n is up there at a billion, a trillion, the two algorithms are basically the same. Okay, they both take a lot of work to write out. Okay, and again, if you have just a single loop, it's going to be big O n. If you have a nested loop, it's going to be big O n squared. Okay, painful but necessary. Okay, this is going to help you out a lot in future programming classes. Okay. All right. Any questions there? Then I'd like to end by doing an example, probably just one at this point, that might help you with your homework assignment. So if you saw your homework assignment, it was a problem sort of like these, a couple of problems sort of like these guys, where you are printing out a pattern, but it's not necessarily going to be exactly this pattern. In fact, one of the patterns you're going to do, if I can just write this down here, is you're going to make a rectangle that's going to be, I think, zeros on the outside. And then X is in the middle. All right, like this. You can actually just do that a few times, and then we're going to say zeros. Okay, so now, how do you do something like that? Okay, the trick is nested loops once again. Okay, nested loops, but now a little bit extra going on. All right, so remember in our first program, we did just let I go from 1 to n, let j go from 1 to n, and keep printing zeros, no matter what. The only difference on this one is sometimes we're printing zeros, sometimes we're printing x's, right? The key is to know when to print zeros and when to print x's. Okay, so what we have to do is kind of, each time we're going to print a symbol, instead of just blindly printing a symbol, we have to make a test. Right? It's one thing or other, a choice between two things. That's what an if does well. All right, so in your original program, here, we printed all zeros. We just said write 0. Instead of just saying write that, we're going to have this inside of an if. Right? So just if something is true, print a 0, else print an x. The key is figuring out what that test is. That's the whole key. Right? So what we're going to do in our time remaining is just a related problem, but that's not exactly the same. And we'll just go ahead and make a new file. And I'm going to save this as stripes.js. Okay, and in stripes, what we're going to do is stripes sub, sorry, nm prints an n by m rectangle, I.E, n rows and m columns, where every other column is all x's, and every other column is all o's. Okay, for example, stripes 6, 5 prints all right, so we're going to start with x's and then go o's. So we're going to say x, 2, 3, 4. Oh, wait. Did we say columns? Never mind. First column is an x, second column is an o, third column is an x, fourth column is an o, fifth column is an x. That's 5 columns, okay? But then the 6 means 6 rows, so it'll be 1, 2, 3, 4, 5, 6. Okay. Do you get the problem now? If I said rows instead of columns, and it'd be the first row would be x's, the second row would be o's, etc. Okay, so let's write the function. Function stripes. N, m. Okay, we would normally do assertions here. Why the heck not? Let's go ahead and do it. Require assert, and we'll say assert that n is greater than or equal to 0 and m is greater than or equal to 0. Okay, now 4. Let I get 1. I is less than or equal to n. That's our rows. I plus plus. Let, 4. Let j get 1. J is less than or equal to m. J plus plus. That's our columns. Okay, print a row, print a column. So keep in mind, as I is increasing, we're printing, when I is 1, we print the first row. When I is 2, we print the second row. When I is 3, we print the third row. Now, as we're printing a single row, j becomes 1, 2, 3, 4, 5. Okay, so before what I said was process dot, shoot, what was the name of that? std out, thank you. Dot write and something like x and a couple spaces. If I do that, it will just be a whole rectangle of x's, right? So instead of saying that directly, I say if some test is true, do x, otherwise do O. All right, so let's build that. We're going to say if something is true, then we do the process x out x, else we do the process dot standard out dot write O. Okay, and then when we hit the end of the J loop, that's the end of the line, so we want the new line. That's when we said console.log. Okay, what's the test? When do we print X? When do we print O? Based upon, well, what variables do we have here? We have N, we have M, we have I, we have J. So we have to have our test based upon those 4 variables. Maybe not all of them, but from that pool of variables. How do you know when to print an X?
J mod 2 equals 1.
Is that right? So we're alternating. So we could say, yes, on the even, since I is starting off as 1, this is column 1, this is column 2, this is column 3, this is column 4. On columns 1 and 3 and 5, in other words, when we have an odd column, we want an X. On columns 2 and columns 4, on even columns, we want an O. All right? So we can just say, yeah. I can't remember what you said. Did you say I or J?
J.
It's got to be J, right? Good. If it's I, then we'd be testing which row we're on. To test which column we're on, we want J. So we say if J mod 2 equals 1, in other words, we have an odd column, we print an X. If the column's not odd, or the mod does not equal 1, the only other option since it's mod 2 is 0. That means even. That means we're going to print an O. So boom, we got it. All right? That's all there is to it. Okay, so if I say here, stripes 6.5.
It's this.
Oops, you're right. And then just for fun, I'm going to test a couple here, console.log, and then I'm going to say stripes. Golly, how about 20, 10? All right, if I run that, I say node stripes.js. My screen is really large, but there's the 2010 one, and here's the 6.5 one. Just like we wanted. Okay, so that was stripes, node stripes.js. Here's the code. So for your patterns on the homework, the test is a little bit more difficult than just this. But think about the one with the border, right? If you're in the first row or in the last row, you want a certain character. If you're on the first column or last column, you want the certain character. If you're anything else, you want the other character, right? So you just have to adjust your if test there appropriately. One thing, as you're getting ready to go, the other homework problem looks like this triangle problem, except it's the mirror image, right? So instead of doing this, you want to say something like this. Okay, and then all right, bear with me a second. Okay, so how do you, yeah, wow.
Add a space.
Yeah, so it's basically what you're gonna do, it's really just like the X's and O problem. But instead of X's and O's, you have spaces and O's. All right, so you can just do the same sort of print a square thing. But instead of printing a square, you're gonna, when you're printing out this particular space, you're either gonna print a space or you're gonna print a 0. You gotta come up with the right test to decide what to print where. Okay. You can do it. I have faith in you guys. Okay, that's it for today. Have a good night. We'll take a look at multidimensional arrays.